1. The core job, resource management. At its heart, an operating system is a sophisticated manager. Its primary goal is to manage the computer's hardware and software resources. Definition: resource. A resource is any physical or virtual component of a computer with limited availability. This includes hardware resources, the CPU, processing time, RAM, memory space, hard disk drives, storage, printers, network cards, etc. Software resources, files, network connections, shared libraries of code. The OS must allocate these resources efficiently and fairly among the various applications and users, preventing conflicts and maximizing performance. 2. The old way, single-tasking systems. This is the most basic method of running programs. Definition: single-tasking. A single-tasking operating system allows only one user program to run at a time. The program continues to run until it finishes its task or is explicitly closed by the user. Detailed explanation. In this model, a program like a word processor takes full control of the CPU. If this program needs to wait for something, like you to press a key or for a file to be read from the slow hard drive, the CPU does absolutely nothing. This waiting period is called an I/O input-output wait. During this wait, millions of potential processing cycles are wasted, leading to very poor CPU utilization. Example: early operating systems like MS-DOS were single-tasking. If you started a command to copy a large file, you couldn't do anything else. The entire computer was dedicated to that one task until it was complete. 3. A smarter approach, multi-programming. This was the first major step towards improving CPU efficiency. Definition: multi-programming. Multi-programming is a technique where multiple programs are kept in the main memory, RAM, simultaneously. The operating system switches the CPU from one program to another whenever the first program has to wait for an I/O operation. Detailed explanation. The goal of multi-programming is to keep the CPU busy at all times. The OS maintains a pool of jobs in memory. When the currently running job, App 1, performs an action that requires waiting, for example, scanf to read keyboard input, the OS doesn't let the CPU go idle. Instead, it immediately switches the CPU's focus to another job that is ready to run, App 2. When the I/O for App 1 is complete, it's placed back in a ready state waiting for its next turn. Example: imagine you tell your computer to calculate a complex spreadsheet, App 1, and download a file, App 2. App 1 runs on the CPU until it needs to save a temporary file to the disk, and I/O wait. Instead of waiting, the OS immediately switches the CPU to managing the file download, App 2. This way the CPU is always doing useful work. 4. The interactive solution, multitasking, time sharing. This is the system we are all familiar with today. It is an extension of multi-programming. Definitions: multitasking or time sharing. A logical extension of multi-programming, where the OS switches the CPU between programs so frequently that users can interact with each program while it is running. Time slice, or quantum. A very small fixed amount of CPU time, typically in milliseconds, that is allocated to a process before the OS considers switching to another process. Detailed explanation. Unlike multi-programming, which only switches during an I/O wait, multitasking forces switches using a timer. This is called preemption. Each application gets to run for its time slice. When the time is up, the OS forcibly interrupts it, saves its current state, and gives the CPU to the next application in line. This switching happens so fast, dozens or hundreds of times per second, that it creates the illusion that all your applications are running simultaneously. This provides a responsive and interactive user experience. Example: you have a web browser, a music player, and a chat application open. The OS gives a few milliseconds of CPU time to the music player to keep the song from stuttering, then a few to the browser to render a web page, then a few to the chat app to check for new messages. This cycle repeats continuously. 5. More power, multiprocessing and parallelism. This involves using hardware with more than one processing unit. Definitions: multiprocessing. A system that has two or more CPUs or a single CPU with multiple cores, allowing it to execute multiple processes or threads simultaneously. Parallelism. The ability of a system to perform multiple tasks at the exact same instant in time by using multiple processing units. Detailed explanation. This is fundamentally different from multitasking. Multitasking creates the illusion of simultaneous execution on a single core. Multiprocessing achieves true simultaneous execution. If your computer has a 4-core CPU, it can literally run 4 different calculations at the same time, with each core dedicated to a different task. Example. When you're editing a video, a multi-core processor can use one core to handle the application's user interface, a second core to process the audio track, and a third core to render a visual effect on the video. This is genuine parallel work, not just fast switching. 6. The sharing problem, race conditions, and synchronization. When multiple processes run concurrently, they often need to share resources, which can lead to problems. Definitions. Shared resource. Any data, file, or device that can be accessed by multiple processes. Race condition. An undesirable situation where the final outcome of a program depends on the unpredictable sequence or timing of execution of multiple threads or processes. It occurs when 2 or more processes access and manipulate a shared resource concurrently, and the result depends on which one wins the race. Synchronization. The process of coordinating the execution of multiple processes to ensure they access shared resources in an orderly, predictable manner, thereby preventing race conditions and data corruption. Detailed explanation. Imagine 2 processes trying to update a bank account balance. Process A reads the balance, $100, and Process B reads the balance, $100. Process A adds $50 and prepares to write $150 back. But before it can, the OS switches to Process B, which subtracts $20 and writes $80 back. Then, the OS switches back to Process A, which finally writes its calculated value of $150. The final balance is incorrectly $150, not the correct $130. To solve this, the OS provides synchronization mechanisms like locks, or mutexes. A process must acquire the lock before accessing the shared resource. While it holds the lock, no other process can access it. When it's done, it releases the lock, allowing another process to take its turn. This ensures serialized access to the resource. 7. The decision maker, the scheduler. With many processes ready to run, the OS needs to decide which one gets the CPU next. Definition: CPU scheduler. The CPU scheduler is the part of the operating system that selects a process from the ready queue and allocates the CPU to it. Detailed explanation. The scheduler's goal is to be fair and efficient. It may use different algorithms to make its decision. For example, it might prioritize processes based on their importance. An interactive process, like your mouse cursor, needs a higher priority than a background task like indexing files to ensure the system feels responsive. The scheduler ensures that high-priority tasks get CPU time when they need it, and that no process is starved of CPU time indefinitely. 8. Protection, isolation, and privilege levels. The OS must protect itself and other applications from faulty or malicious programs. Definitions: isolation. A principle where the OS ensures that each application runs in its own protected memory space, preventing it from interfering with other applications or the OS itself. Kernel mode, ring 0. The most privileged execution mode for a CPU. In this mode, the code, the OS kernel, has unrestricted access to all hardware and memory in the system. User mode, ring 3, a restricted, unprivileged mode where user applications run. Code in this mode cannot directly access hardware or critical system memory. System call, the mechanism used by an application in user mode to request a service from the operating system kernel in kernel mode. Detailed explanation. Your computer's CPU has at least 2 modes. The OS kernel runs in the all-powerful kernel mode. All your apps, browser, games, etc., run in the limited user mode. If your browser wants to do something privileged, like connect to the internet or save a file, it can't do it directly. It must make a formal request, a system call, to the OS. The OS then switches to kernel mode, validates the request, performs the action safely on the app's behalf, and returns the result. This strict separation prevents a crashing app from bringing down the entire system. 9. Security, access control. Security determines who is allowed to do what. Definition: access control. Access control is a security technique that regulates who or what can view or use resources in a computing environment. It is the process of granting or denying specific requests based on the user's identity. Detailed explanation. This is managed through permissions. After you log in authentication, the OS knows who you are. Every file and resource has an associated list of users and what they are allowed to do. For example, read, write, execute. When you try to open a file, the OS checks if your username has the required permission. Example: on a university server, a student's account may have permission to read a professor's lecture notes but not write or delete them. The professor's account, however, has full read, write, and delete permissions for that same file. The OS is responsible for enforcing these rules.